Hello, everybody. My name is Matthias Lorick. I'm an electromagnetics simulation specialist here at RAND Simulation. Just a little bit about RAND Simulation. We are an Ansys certified elite channel partner. And so we are able to provide you with engineering simulation solutions to tackle some of the difficult problems surrounding all engineering. But for specifically today, we're going to talk a little bit about electronics reliability and the challenges associated with it, and how simulation can help with easing that burden and also assisting in driving educated design decisions. So just a quick little agenda here. First, we're going to just do a quick overview of electronics reliability. So what is electronics reliability? What are the different types? Why do we care about it? And really the case for why we should be considering doing reliability simulations. And that's going to branch into a solution that I'd love to talk about, which is Ansys Sherlock. Sherlock is a electronics reliability tool, specifically for PCB evaluation, and some of the things that we're going to go into are thermal analysis, vibration, time to failure prediction, and how that can assist us to drive educated engineering design decisions. So let's go right into it. What is electronics reliability? Well, the definition of electronics reliability is down there at the bottom. It's the probability that a piece of electronics equipment operating under specified conditions will perform satisfactorily for a given period of time. So you design a product, you sell the product, it's out in the field. Every product is going to have an estimated lifespan, and we want to make sure that the design is able to satisfy that lifespan that's advertised, making sure that we're not having warranty claims or unhappy customers. But what are the different types here? And so we have these up here on the screen. And so there's kind of three different sections of where reliability is important. So there's performance, and in performance you have power. So how much power is my design using? Is it using more than it needs to? Maybe it has inefficient power supplies, or maybe there's a concern that over a certain amount of power, the associated peripherals aren't going to no longer work, or it's going to overload a power supply. Or for example, if we have a really high-speed data bus on our design, how well is that data going to be pushed through? Are we really getting 112 gigabits per second on our PAM4 lines, or is a signal integrity associated issue driving that data rate down? And then the life. Is it going to live the 10 years or however long that we specify we want our designs to last? Now, the second section of electronics reliability is safety, and this is really important because this actually has implications on both people as well as other devices in the environment. And so thermal reliability, is it going to operate within the range that the design is specified for? So if you have an automotive component that fails when it gets cold, that could have very critical impacts on the system and potentially the safety of the vehicle itself and the passengers that are within. And then EMI and EMC. So this is really common when you're dealing with getting through that carrier's regulatory certification process. Is my device making too much noise to pass? Is it going to interfere with other devices, or is it going to have implications that are negative on the performance? So if you have a medical device and it's susceptible to EMI, then it may operate incorrectly and cause issues. And then the mechanical reliability. There's standards, whether it's military or IP, that are necessary to be withheld for those safety points. And then the last one, from a business-driven perspective, is cost. Can we make the design smaller? A smaller design means we're going to be able to fit more panels or more PCBs onto a given panel. Are we able to reduce the BOM? That's going to reduce the cost, obviously. And then defects. We want to have a high yield first pass. Otherwise, you're going to have redesigns. That's going to have additional issues. And defects in tooling, same thing. We want to avoid having any unnecessary costs through the design process wherever we can, and that's where some of this simulation is going to assist us. And so why, again, just to kind of reiterate, why is reliability analysis important? So like we mentioned, so increasing the number of features in the design. As we make things more complex, we need to make sure that, maybe the existing design was able to support that. We want to have a lower BOM cost so that the profit margins on the product are increased. We want to maintain our engineering headcount. We want to make sure that we have engineers that are, consistently able to move on to additional projects and grow the business, grow the technology. Time to market is key. There's, depending on, the industry that you may be in, those launch windows are very tight, and we want to make sure that anything associated with the failure of a PCB are mitigated to reduce that portion of the time to market impact. Improving the first pass yield. Everyone loves to get a first pass board spin, whether it's passing EMI and passing DFM. And so we want to drive for that as well. We don't want to have our designs returned. We don't want to have a bunch of field failures halfway through the expected life cycle. And this last one is kind of, common now. And so this is another thing that I want people to think about is, the component shortages that's going on right now in the semiconductor industry is impacting, nearly everybody. And I've had conversations with numerous customers where they are having to redesign their boards to facilitate a different component. So for example, they couldn't get their microcontroller because it went from $3 to $40. So they swapped it out for something different, but the pin orientations are slightly different. So they have to, respin their board. Using the electronics reliability simulation to prove out those designs helps them get back into production quicker. And so I imagine most of you are familiar with the traditional or typical electronics design process. So starting up here on the upper right, you will design your board, you'll build your prototypes, you'll test it, whether that's EMI or mechanical testing, so environmental, thermal, vibration, and then you're going to break the design. Either it's going to fail or it's going to have an interoperating mode, and then you go through the process of fixing it. And 73% cost is associated with that test, fail, fix, repeat cycle. And so we want to reduce just going around in the circle over and over again to reduce that cost and to get the board ready faster. And so this is kind of a nice thing to look at here is, how do we quantify the impact of simulation on electronics reliability? Well, the first thing is that, there's accelerated life testing, whether that's vibration, thermal cycling, thermal shock, but those still take, sometimes several weeks to, upwards of a month to actually run the physical test. And so you're going to see up to a 2400 X acceleration of simulation time with reduced order models. And so by simulating as opposed to testing or using it prior to testing, you're not going to have to go back to the lab a second time after you've made that break, redesign, repeat cycle. And we're seeing a 75% on average reduction in hardware design cycle because of this. And we're seeing a 20% reduction in material costs associated with that. So every board spin costs, several hundred to several thousands of dollars. Same thing with components. Anywhere that we can speed up the development and reduce the cost associated with it is where this is going to really shine through for us. And so in comes Ansys Sherlock. And so there's, like I've kind of already discussed, there's a lot of different avenues of where electronics reliability comes into play. But what we're going to be talking about predominantly today is Ansys Sherlock. And so what Ansys Sherlock is an industry-leading reliability physics analysis tool for electronics, specifically PCB assemblies. And what's good with Sherlock is that it helps us mitigate issues associated with thermal, shock, vibration, solder fatigue, issues with this design for manufacturer, issues associated with in-circuit testing, so flexion associated with putting it into the test fixture. And what's nice with Sherlock is that it works as its own standalone tool. But if you maybe have other additional Ansys tools as well, you're able to link some of those together to build out and build an even more refined analysis of your design. And some of those tools include SpaceClaim, IcePack, and Ansys Mechanical. And so the first thing that you're going to do once you're into Ansys Sherlock is you're going to actually import in your design. And so when you are doing your layout in whatever layout tool you specifically use, two common import types for Ansys Sherlock are the ODB++ and the IPC 2581. There's some additional ones as well. So if you're curious about some of the other import options, let's have a discussion about that at another time. But the most common one that we see is the ODB++. And so what the ODB++ includes is it will have the components, it will have your test points, your mounting points, the locations of where you are not necessarily in the ODB++, but you can assign where you put your test fixture points. It's going to have all of your nets, and it's going to have all your copper on the different layers for analysis. And what's really nice here is that you're able to model some of the really refined things like potting, thermal paste, wire bonding, heat sinks, some of those things that are most certainly going to have impacts both from a mechanical and thermal perspective that you want to be capturing in a simulation like this. And what's nice as well is that once you've edited or imported in your PCB archive, you're able to make revisions to this design. And so since this is in the interface, once you've run an analysis and say you find that you have some flexion right in the center of the board, you're able to move these components around and place them in different locations, or you could do a what-if scenario of what happens if I add another mounting point at different spots as opposed to just in the corners. You're able to do this within the tool itself so that you don't have to go back and make changes in your layout itself and then re-import that in. You're able to make those edits on the fly within Sherlock itself. And so once you've already looked at your PCB, it's always a good check to also review the Stackup. And so the Stackup also has a lot of interesting properties, a little bit more so than you may necessarily be familiar with if you're working in your layout tool. And so a couple of the parameters that you'll see here are, your board dimensions, your board thickness, the density of your board, the number of conductor layers, and then a couple of these parameters that you may or may not be associated with. So this CTE is the thermal expansion in the XY and the Z plane, and then the EXY or EZ is the elastic modulus. And so that's going to be dependent on how elastic your board is, how susceptible it is to flexion or vibration, and then how susceptible is it to thermal expansion. This is all going to come into play when you run the analysis through Sherlock for a thermal or mechanical analysis. But what's neat as well is that, if you look here on the different layers, you'll see that it has this little percentage associated with it. And what that is that when Sherlock brings in your design, it's calculating how much of the copper is present on each layer. And it will adjust the thermal expansion and elastic modulus accordingly based off of those parameters. So for example, if we look at layer 7, the signal layer, but it only has 1.6% copper present, and it has a much lower elastic modulus as opposed to a layer, the power layer, that has 94.7% PCB coverage. And so this gives you insight as to how populated or how impactful the density of routing or power planes or ground planes will have impact on the different layers. But also it's taking all of this into effect. So it's not just taking a smoothing, mean or average of the total weight or density of your board and running the simulation on that. It's actually looking through layer to layer to calculate through how that flexion may occur. And so once we've gone through the layouts, we've gone through the Stackup, then we want to look at our parts. And so these parts will come in with the archive. But what's really amazing with Sherlock is that Sherlock actually has a library of thousands of standard components. I think the last time I remember reading it was, I think, over 50,000 at this point. And what this is able to do is that it will automatically match to the part number in your design, and it'll check it, cross-reference against it to the Sherlock library. And so what that's doing is that's bringing in all the relevant part information, the dimensions, the pad sizes, anything that's relevant to the part itself that will be used in the different reliability simulations that you would be applying. And if those don't, if you happen to have a unique part and it doesn't exist in the library, it's the Sherlock library itself, you can always revise and customize parts and add them to, what's called your user or your local component library. So once you've brought those parts in, for example, if you're using this tool and you have your own internal parts database, you can import in all of those parts, assign the parameters accordingly, and you have everything that you need to go to run through a simulation in Ansys Sherlock. And so here's a little bit of a deeper dive into what some of those part properties look like. So you've got your part type, you have your part number, manufacturer, and then some of the interesting ones that are actually going to build off of into the later parts of this presentation are, solder thickness, the leads or pads or balls on a BGA, how that's impacted, how that's designed, what the power, current, or voltage ratings are of the components, as well as the thermal rating of the component. And you're also able to see the 3D representation of the component as it's shown. And you can customize this to incorporate the pads or the balls underneath it. You can keep it relatively simplified. It's really kind of up to you how far you want to customize the analysis and drive towards more accurate results. And so once we've imported, we've looked at all of our parts, we've checked our Stackup, the first thing that we need to do is we need to kind of set an objective. And so the overarching objective, if we boil down it to one sentence for a PCB reliability, I want my design to be in the field for this long, for 10 years, and I want it to have less than a 20% probability of failure. And so what we're setting here is we're assigning our service life and we're assigning our probability of failure. And this is going to come into play in a little bit because in some future slides, we'll see some graphs that are showing the plots of over time what the probability of failure is of the design due to different reliability simulations. And so the service life is just the expected duration of the product. We set that in any timeline we want. We can set it in years, days, months, and then we assign our reliability metric, which is what we're showing here, the probability of failure. And then once we've set up that overview, we then go through and start creating our profiles. And so what these profiles are going to do is they're going to be leveraged in the different analyses within Sherlock. And so we have thermal profiles, we have vibration profiles, we have shock profiles. And so the first one that we're looking at right now is the thermal cycling profile. So you may be familiar with, there's a hold time down at 0, and then it ramps up for a certain amount of time, and then it holds at a certain temperature, and then it ramps back down, and then it will just repeat that over and over again. And so what we're looking at over here is we can set how many cycles we want to go through, and over here we can set that temperature profile itself. If we have something specific that we want to import, we can import in a text file that has all of this relevant information. Or if you just have the profile from a test standard, it's just a simple, charting of what we're going to plot here. So you can create pretty much any sort of thermal profile that you want. Moving into the random vibration. So random vibration, it's going to have a random vibration. And so what we can do is we can specify how long we're going to let this run for, how many times we're going to run through that cycle, and then we can specify, whether we're doing it in the X, Y, or Z. Usually you'll have to do it in multiple orientations. And then you can specify the profile again. So at different frequencies, you can set frequency-specific loads that are associated, and you can develop this profile. Just like in the thermal analysis or the thermal cycling that I just showed you, you're able to customize this, save it, import it in for future use as well. So if you have a standard test profile that you run all of your designs through, you go to the lab, you book the, weeks in advance, the big slot of time that you have all your designs, what profiles and what things are going to be tested. You can create all of those and reload them so you don't have to continue to do this over and over again if it's a common test. And then one thing that's also kind of neat as well is that if you are interested in doing some deeper analysis, you can actually assign a PCB orientation offset. So the load is going to move in the X, Y, or Z direction. But if you're interested in maybe a really tall capacitor, or maybe some component that's on your board that is maybe leaded, and just the way that, or maybe how the design may be mounted in the field, you want to see an assignment of that load in a off-axis perspective, you can assign relevant angles in that regard to accomplish essentially any sort of orientation of your design that you would like to see for something like this. And then like random vibration, we can also run through harmonic vibration. So instead of it just occurring randomly, we can also specify specific loads at specific frequencies or sweep through to accomplish a similar effect. So if you have a certain frequency that you're operating at, so say for example, or that your environment's going to be impacted by, so maybe for example, if this is going to go on an aircraft, there's a profile of the harmonic frequencies associated with the airline engines, and so you could run a harmonic vibration analysis at those different frequencies at various loads to understand what that might look like in your end result. And just like in the other vibration analysis, you can customize and save these profiles as well as orienting it off the PCB axis. And then the last primary setup that we have here is the shock event. And so this one's kind of neat because this one has a lot of user customization associated with it. So just like the other ones, you have your load direction, your PCB orientation, your duration, the number of cycles. But what's cool is that when you're actually going into the editor, you aren't limited to just a assignment of this. So you can specify your frequency, you can specify your load in G's. But then what's also neat is that you're able to assign a decay. So for example, this sampling rate is the pulse duration is 10 milliseconds, but maybe you want to see how it settles out after that. So you can assign a decay. So then instead of this looking like a pure half sinusoid, it could look more of like a spike and then just decay off. And so that will, give you a snapshot into, how that pattern is going to change. And then on this next slide, here are the other available default pulses that you can therefore adjust the loads and decays to. But so you're not just limited to a sinusoid, you have a number of different, full sinusoid, triangle, sawtooth, square, etc. And so you can really kind of put it through its paces and try a lot of different shock events outside of just a simple pulse. And so now that we've set up all of the different initializations, we actually can start going through some of the actual analyses that Sherlock has to offer for our PCBs. And so the first one we're going to talk about is solder fatigue. So solder fatigue leverages that thermal cycling setup that we were going over. And what it's looking at is it's also taking into account the amount of solder on each of the given components as assigned in those component assignments. And so what we see here is the breakdown of, good, a little bit of a warning or concerning, and then bad. And this is giving us a list of the number of components that fall into each range. So the color code indicates the number of components and the risk they are for solder fatigue over temperature. And then over here on the right is what's called the life prediction. And this is going to come up quite a bit for the different designs. And this is what was tied into that life cycle setup that we were discussing earlier. So you can see here we have a lifetime of 10 years as we specified. And then we have a probability of failure percentage that we specified at 20%. And so for it to be considered passing based off of the criteria that we specified, we want this red trace to be leaving out through this right side of our little rectangle that we've specified. If it cuts through the created x-axis at 20%, that's considered a failure. That's something that we need to consider. This is telling us that at 5 years in to our 10-year duration, we're going to expect to see 20% of those designs failing. And then at 10 years, we are up to 85 or 82.5%. And then at 15 years, all of them are expected to have failed due to the solder joint fatigue. So based off of this, we could go back in, we could change the way that that solder joint is applied to flatten this curve and bring that in within the realm of what we want to see. And then moving into a little bit more of a breakdown for solder fatigue is a distribution. So you can see where the different parts are going to fail over the time in years. So we have some that are expected to fail predominantly in that 8 to 10 year range, some up at 16 to 20 years, and then we have a couple up at 48 and 50. But what this is showing us is where the breakdown of the different components run into play. And so what this is, and then this is a representation of it in a table over on the left here. And so what that means is that we can kind of have a short list of the components that we need to worry about. So maybe we need to replace those with a higher temperature rated component, or maybe we need to look at how they are placed and related to other sections, and maybe look into doing some sort of application of a heat sink to get some of the heat off the board. But this gives us a list of the components that we're most concerned with. Ideally, we want to have all of these obviously out, beyond the service life of 10 years, but it's also useful to see which ones are, really of less concern because, this is at 20 years, this is at 50 years. We have components that are expected to last into that range for solder fatigue. So that's good. We just want to have as many over to this right side as we possibly can. And then another thing from the thermal perspective is thermal derating. And so any thermal cycle where, based off that thermal cycle, we specified we wanted it to be at 125 C at the peak. What thermal derating is looking at is it's taking the derating associated with a component, which is paired with its max temperature, and then it's comparing that to the thermal cycling profile that we've created. And so in this instance, we've found that since all of our components are rated at some of them are rated at 125, our max temps at 125, that doesn't give us any margin, so that's considered a failure. We also have components that are only rated to 85 C, and we go up to 125 C, so those are obviously a failure. This is going to give you a very quick breakdown of all the components that are in compliance with the temperatures that you want to subject to the device. And so the next analysis that we can look at is what's called the natural frequency. And so what the natural frequency is taking into account is it's taking into account a couple things. It's taking into account the PCB from a copper density perspective on the different layers. It's taking into the account the physical dimensions of the PCB, as well as the mounting points. So as you can see here, the mounting points are in these four corners. And what the natural frequency is doing is it's sweeping over a user-specified range of vibration of resonant frequencies, and it's generating the different modes that pop up, and it's giving you the representative frequency at that point. So if you knew that you had in your source design or your source system, so then back to the aircraft analogy, if you knew that you had a 500 hertz resonance at some location where this PCB is going to be applied, that is a concern. That is going to be something that you need to mitigate. And what's useful as well is that on this right side here is this is the 3D visualization of how that PCB is going to flex due to those natural frequencies. So we have two ICs right here in the middle. That's particularly concerning to see that the resonant frequency is predominantly here in this center. So what could we do to improve this? You know, maybe we could add an additional mounting point somewhere near the middle to prevent that flexion right at that spot. And then we would rerun this analysis. We would get a new list of natural frequencies, and we would get a new 3D visualization of that flexion associated with it. Other things that could improve this as well would be moving around where your components are placed. But really, it's most common we see is just changing where those mounting locations are going to occur is going to have the biggest impact, or changing the dimensions of your PCB itself. So this is really common. So for example, if you have a design that you're trying to miniaturize, you know, you've proven out the large design, but now that you're going to a smaller one, maybe there's something that, you know, is going to pop up, or, you know, maybe probably more commonly, if you have an existing design and you want to add functionality to it, so you're growing the size of the PCB, you know, now you might be bringing into some additional natural frequencies that you weren't concerned with in the past, and that you need to address with some of these mounting location methods. And so using that mechanical shock profile that I showed you earlier, and so if you recall, that mechanical shock was a 30G load over 10 milliseconds in the positive or in the negative Z direction. And so what you see here is the three-dimensional representation of the displacement in millimeters due to that mechanical shock. And again, as expected, we have the mounting locations in the corners. So the flexion is going to occur predominantly in the center. And just like in the natural frequency, we have concern where this is going to cause solder joint failures associated with different components. And that's exactly what we're seeing down here in this table. So in this table, it's telling us which components are going to be impacted by the mechanical shock and what the probability of that failure is per cycle. And so based off of those probabilities, we're then able to generate a mechanical shock life prediction based off of you know, a lifetime that we specified. So for in this example, we changed the lifetime to 5 years, but you can see that when we change that, when we run this analysis, we're seeing that, you know, 20% of the devices are going to be failing in the field before year 2. And so we want to avoid that wherever we possibly can. So again, adding some changes to the design to increase robustness is going to only help you in this resolve. And what's great about simulation is that, you know, whether you have, you know, specific automotive standards that you have to test to, or you know, if you have to go to the lab because of, you know, regulatory or requirements within your design specifically, that's fine. You know, the lab is always a good thing to give you that, you know, true analysis. But what is good with simulation is that in the instances where you don't have to go to the lab, or instances where you only have the budget and the time to go to the lab once, this is where leveraging these types of simulations really comes into play, because you can see what you expect is going the lab result to be and make the necessary changes before the design has even been fabricated, so that you have all of these, your bases covered before the designs are made and before you go to the lab for your official testing. And so this analysis is a thermal mechanical analysis. And so what that means is using that thermal profile, this is showing mechanical strain associated with heat. So you'll see that the concentration of the heat is in the mounting locations, but then protrudes through different parts of the board. So this is going to be due to copper density, the location and density of different components. And so we want to reduce the strain wherever we potentially can, but it's also giving us insight as to, if we have a design that is getting hot, or it's in an environment that is hot, but it has components that are really susceptible to, mechanical strain. So think BGAs again. This is going to be useful to understand, are these two big ICs in the center at high risk due to, its environment? So if this is, deployed in Arizona, we want to make sure that this has a limited thermal expansion profile so that it will operate as we expect. One thing as well is that you can also couple this type of analysis with a tool called Ansys IcePack. And what IcePack is looking at is the thermal properties specific to the traces and components on your design. And so you're able to assign, the loads and the currents associated with the components in IcePack and bring that into Sherlock and give yourself an even more refined understanding of how the additional heat associated with your board operating is reflected in the simulated reliability environment of the thermal cycling. And so that's a topic that we intend to go into a deeper dive with a future webinar. So be on the lookout for that in the future. But thermal mechanical kind of gives you the mechanical insight associated with how your board reacts to heat. And so the random vibration, you can see here when we run it through the random vibration profile, you get another pretty cool looking three-dimensional representation of how your board is impacted by that random vibration, where the strain is maximized, and you can kind of see a couple spots. You have your mounting points, but then you also have it along both edges of where these these two BGAs are soldered down. And so, we get a passing predicted life value. We're only hitting, about 12% once we're at 10 years. And we have the, one not populated component, it's a connector that, has 11% probability of failure over, that span of time. But so it's passing, it's not a concern. But this is where it's important to also think about part editing. So when it comes to like a BGA, you can bring it in and you can run your analysis. But if you want to further refine it, if you want to get a more accurate representation of how those different solder balls are impacted, you can go in and edit the part and save it back into your local library and make different changes to some of the parameters like the ball diameter or the ball package size or the height. And what this is doing is this is bringing in more fidelity to these specific components. So ones that are really important, like memory chips or like microcontrollers, onboard, CPUs, anything that has a BGA, this is going to be really important. And I want to kind of go back to the discussion about component shortages. So, as we kind of think, I think we're all kind of feeling that pain in some way or another. And when you're swapping things out, specifically, silicon stuff like ICs with BGAs, from manufacturer to manufacturer, there may be a little bit of a variance in what those solder reflow patterns or those the solder paste layouts look like. And so if you just use if you take your design process from from manufacturer A, and then you switch your part to manufacturer B because you have the shortage in manufacturer A, you want to make sure that if there are some changes in the land pattern or the ball size associated with that other part, you want to make sure that you're capturing that. So if you had gone through vibration or flexion studies before with your original design, and now you're having to put in a new part, it's important to look at that because, you know, maybe that those minor variances that would have a impact in maybe the yield of your new design. And so what we're doing here is we're just adding more fidelity to the balls themselves, and then we're repeating the random vibration. And now when we did that on this part right here, and you can see now we actually have the modeling of the individual balls on this BGA. And when we added that additional fidelity, now we have a concern. Now we're seeing a 20% drop off at 2 years, and it's indicating to us that U10 has a 100% failure probability before of 10 years because of random vibration. And so we need to reduce this vibration by either changing the solder properties, which we may have limited ability of doing because of the manufacturer recommended dimensions for that. And so we have to go back and look at, see what can we do on our design that we have control over to do that. And that includes making different changes to the component placement. So it could be potentially, you know, moving this component out of the center where this flexion is the largest, maybe moving it off to the side, or adding some of those other things like a mounting point or something else that would reduce that impact the impact strain due to random vibration or any analysis that we're looking at for this. And what's nice again is that you can make those what if changes inside Sherlock, so you're not constantly making one little change in your native layout tool, generating a whole new ODB++ or IPC file, importing it all in and setting everything back up. You're able to do all this within your existing workspace of Sherlock. And so once you've run through all of the different analysis that you're interested in, you're able to get a overlay of all of the different time to failures that you evaluated. And so we've got our thermal cycling due to solder fatigue. We have PTH, plated through hole thermal cycling fatigue, vibration fatigue, constant failure rate associated with, you know, the component database. We didn't really touch into that so much, but, you know, if we take these three right here, and it's going to give us a blended equivalence of overall combined risk. And so, you know, maybe we're not plotting all of these on this page, but what we're seeing here is that you get the end all. This red trace, for example, is where our issues are going to, you know, this is the true understanding of how many boards we're going to lose before our expected lifespan. And so I covered the most prevalent analyses within Sherlock, but there's a couple other ones that I want to mention as well. So there's the InCircuit Test. So you're able to place your different pogo pins or your test points that are inside your test fixture that is going to be at the manufacturing house, and see what the flexion associated with that is when you close the lid. I've had issues in the past where we've had failing boards that were, you know, half of them would work, half of them wouldn't. We figured out that it was that flexion on the manufacturing test or the install that caused those solder joints to break. You have CAF failures, PTH fatigues, semiconductor wear out. You can also, you know, with all of these different analysis, also create a DFMEA analysis. If that's part of your traditional workflow, you're able to integrate that in to Sherlock and build out that report. And then, like I mentioned earlier, you're able to revise your thermal simulations with an electronics losses and heating link with Ansys IcePack. And so the end result of all of these different types of simulations in Sherlock is to ultimately drive design decisions to build the most robust and reliable electronics PCB that you possibly can. And so based off of the outputs of the different simulations, we have, you know, some decisions to make to either fix things or understand where we could potentially relax some of the requirements to accommodate something that may have an issue. So when we're thinking about solder fatigue, common is going to be, changing the pad size. So you're going to get more solder on that joint, and you're going to, therefore have a longer expected life for the solder. Going into the package, the same thing, changing that package to either have a larger land size or have a larger space so that it's able to dissipate the heat within the package itself better. That's going to improve upon that solder fatigue. Or changing the PCB properties themselves. So changing the, how you have the solder mask applied, or what the type of laminate, or maybe the density of the copper, or changing some of the way that things are routed is going to have impacts on all these things as well. Some things also that aren't mentioned here would obviously also be just component placement. So how dense is it in a certain region, or is it close to, if we linked it to ice pack, how close is it to a very hot heat generating component? Things like that allow you to make the decisions prior to fabricating and ensuring that your design works as you expect and is reliable. And so in summary, Sherlock's going to help you avoid redesign and retesting due to failures from temperature, power cycling, vibration, and mechanical shock. It's going to eliminate manufacturing defects and will ensure that your board has is quality and is reliable throughout your electronic supply chain. So you're making sure that all of your components are going to operate as you'd expect. Just checking all of those boxes up front so that you know that you have a solid design. It's going to increase your first pass yields during manufacturing. It's going to reduce the warranties and it's also going to allow you to assist in warranty planning. So if you have that life, the expected life chart, it's going to maybe allow some of the decision makers within your organization that make the decision around warranty decide how many years should that warranty be. Or if we don't want to have a 10-year warranty if we know that 100% of our boards are going to fail within 5 years. It's going to allow you to predict at the board level and assess risks with the different analysis that we mentioned, so shock, vibration, thermal, and some other conditions that we mentioned. And it's the best-in-class modeling is great. So like that ball grid array example that I was talking about allows you to model it down to the actual solder joint to give you that greater fidelity. And then that links into Ansys Mechanical, Dyna, or IcePack to further build out your reliability analysis. And so last but not least, if you have any questions, or if this was interesting to you and you want to learn more about Ansys Sherlock, the team here at RAM Simulation is more than happy to help you out, have a conversation. And I appreciate your time and attention today. And now I'm going to take it over to questions.